Okay, so in this video we're going to talk about the last part of this unit, which is solving problems with two-object problems. And basically what we're going to be talking about can technically be extended to problems with more than two objects, but typically you don't see more than two or three at the most objects just because it gets kind of a lot to keep track of. Okay, so like any second law problem, we're going to follow the same basic process. We're going to draw a free body diagram. We're going to write out our second law equations to determine acceleration, and then we're going to write down the sum of the forces on the left side of the equation. The only difference is now we're going to do it for two objects instead of one. And what makes a two-object problem unique is you have two objects interacting with each other. And so most of the time when you're doing a two-object problem, you have Newton's third law come into play. And just to remind you, Newton's third law says for every action, that means for every force, there is an equal and opposite reaction force. Okay, and so keeping that in mind, we're going to do 3 examples for two-object problems, and then we will be done for the rest of the semester. Okay, so let's take a look at example 1. And this is a very basic example of a two-object problem. Okay, so it says 2 buckets are at rest as arranged in the diagram below. Determine the tension in each rope. Okay, now we're going to start with drawing a free body diagram for these two objects. And just to be able to label these something, I'm going to call the top one, I'm going to call that mass 1. I'm going to call the bottom one mass 2. Okay, now when I'm drawing, I'm going to draw this this FBD first. Now, the objects are at rest, which means they have a net force of 0. And so mass 2 has a force of gravity. I'm going to call that Fg2, force of gravity for mass 2. And of course, it has tension in it because it's connected by a rope. And since this is rope number 2, I'm going to call this Ft2. Okay, and that's obviously what is holding mass 2 up. And those two arrows should be the same length. If they're not, it's just because of my bad drawing skills. Okay, now, that's a pretty simple FBD. Mass 1, on the other hand, this FBD is a little more subtle because there's 2 ropes physically touching mass 2. So the FBD for mass 2 looks like this. We have force of gravity going down, Fg1. And there's very obviously tension in rope number 1. And I'm going to call that Ft1. However, notice that rope 2 is pulling up on the bottom mass. However, it is pulling down on the top mass. And so mass 1 actually has 2 forces going down. Okay, so I'm going to draw a second arrow going down, and that force is Ft2. And this Ft2 and this Ft2 are the same force. Okay, so why does the same force appear on 2 separate free body why does the same force appear on 2 separate free body diagrams? Because of Newton's third law. Okay, what you're seeing there is a third law reaction force. Okay, so these 2 tensions are equal and opposite to each other. Okay, same magnitude, opposite direction. Okay, so top mass has 3 forces acting on it, bottom one has 2. So now I'm going to, for Newton's, I'm going to apply Newton's second law. And so I'm going to write out my second law equations, and I will do it for mass 2. I'm going to do it for mass 1 first. So I have F net y equals m1 ay. Determine acceleration. Is the object accelerating? No, because it's at rest. Write down the sum of the forces. So for mass 1, I have Ft1 going up. And I'm going to write minus Ft2 minus Ft2. Now, why do I put a minus sign if I should be doing the sum of the forces? Because I know that this Ft2 is going to be negative based on the direction. And so that minus sign is to remind myself that Ft2, this Ft2, is going in the negative direction. And likewise, I'm going to put minus Fg1 right here. Again, this minus sign is just to remind you that this Fg should be negative. Okay, and so when I get to calculate Fg1, by the way, Fg1 would be m1 times g, and I multiply by the acceleration due to gravity. What I'm doing is I'm doing 10 minus negative 10, and that's negative 100 newtons. What number do I plug in here? Minus 100 newtons. Okay, in other words, this negative sign is already taken into account this negative sign up here because they both represent direction. Okay, so the back part of this equation is just going to be minus 100. Now, for mass 2, when I write down the second law equation, I have F net y equals m2ay, still at rest, so the right side is 0. There's only two forces acting on rope 2, and that is Ft2, which is now acting in the positive direction, because it's holding the bottom mass up, minus Fg2. And again, this minus sign is only to indicate direction. The direction of this force is down. Okay, so when I go to calculate Fg2, that would be m2 times g, and I get 20 times negative 10 equals negative 200 newtons. When I actually go to plug in, I'm just going to put minus 200 newtons. I'm not going to put minus negative 200 newtons, because this minus sign and this minus sign both indicate that the direction of the force of gravity is down. Okay, so don't overthink this. Now, what I'm going to do is I am going to write out basically my two equations. I have Ft1 minus Ft2 minus Fg1, which is negative 100. Okay, so minus 100. Again, I'm not counting that I'm not double counting that negative sign. Okay, this negative sign represents direction. This negative sign represents direction. I'm not subtracting a negative. They both represent the same thing. This equation down here, I have Ft2 minus 200 equals 0. And if you look at what I have a system of equations. Anytime you're doing a two-object problem, whether it's like, this type of problem or a pulley problem, you always end up with a system of equations because you basically get one equation every time you apply Newton's second law. And so if you have more than one object, you get a system of equations. And so I have two equations and two unknowns. And notice that the way I've written this is it's set perfectly to solve using elimination. Okay, so I'm just going to clear a little space for myself to solve this by elimination. The way elimination works when you're solving a system is you basically just add the two equations together. When I add the top equation to the bottom equation, this cancels, and I end up with Ft1 minus negative 100 plus negative 200 is negative 300 equals 0, and so Ft1 equals 300 newtons. Now, this result is not at all surprising because it is exactly what you would expect, because you can think rope 1 has to support two masses and the combined weight is going to be 300 newtons. Okay, so even if you didn't do the problem like this, you could probably get 300 newtons for Ft1. But the tension in the bottom rope is where you really need to have applied the second law correctly. Because now that I have Ft1, I have to have the second law equation to solve for Ft2. That's the tension in the rope number 2. So now that I have Ft1, I can go back in, substitute back into this first equation, and I get 300 minus Ft2 minus Fg1, which is 100, equals 0. And so you find Ft2 in this case is negative 200 newtons, and this negative sign only indicates direction. Okay, and so in other words, what I'm saying is, actually, did I do that correctly? Let me just make sure. No, that should be positive 200 newtons. Okay, so the tension in rope number 2 is 200 newtons. And so I have found two tensions. I have answered the question. I'm done with example 1. Okay, so that is an example of a two-object problem. And again, you don't need the full-on two-object analysis to find the tension in the top rope, but you kind of do to find the tension in the bottom rope. Okay, so pause there, make sure you add that to your notes. We will do two more examples with two-object problems. Okay, so example 2. Says a locomotive pulling a freight car accelerates at 0.5 meters per second squared as shown in the diagram. I think this question is actually an AP physics question, but it's still good for our purposes. And the question is, actually, before I even look at the question, let me just follow my second law process. I have two objects. I have the freight car and the locomotive. And so I'm going to draw the FBD, and I will do it in a different color because the picture is black. Okay, so what are the forces acting on the freight car? Well, the freight car has a force of gravity going down. I will call that FG2. I'm just going to call this one mass 2 and this one mass 1 just because this one is, first and this one is second. It doesn't really matter what you call it. Okay, so the freight car, I'm going to call that force of gravity FG2. It obviously has a normal force because it's on a surface. I will call that FN2. And focus on what is pulling, or what is physically touching this object. Okay, this object is being physically touched by this conductor right here. Okay, and so there is a force from the coupling. I know it's called the coupling because the question is asking me about the tension in the coupling. You can either call it F coupling, or since it calls it tension, I guess you could also call it tension. So I'm going to call that FT. Now, what does the FBD look like for the freight car, or sorry, for the locomotive? Well, force of gravity going down. I'm going to call that FG1. Normal force, not the same normal force, so I call it FN1. There is very obviously a force from the engine making the locomotive accelerate. Now, does it say anything about an engine? No, but why else would the locomotive be accelerating? Okay, so it's just kind of common sense to understand that has to be some force from the engine or the boiler or whatever you call it. Something is making the train accelerate. Okay, now there's not three forces, but there's actually four forces on the locomotive. Okay, the fourth force comes from the tension in the coupling. The tension in the coupling is pulling the freight car to the left. But because of Newton's third law, for every action there is an equal and opposite reaction. That tension pulls the freight car to the left, but it also pulls back on the locomotive to the right. And so there's also Ft pulling the locomotive back to the right. And so we see two forces that are equal and opposite showing up on two separate FBDs. That is Newton's third law at work. Okay, so the coupling, in other words, the locomotive pulls on the freight car pulls back on the locomotive with an equal and opposite force. Okay, so the locomotive has four forces on it. The freight car has only three. Now it says we can ignore friction, which is really helpful actually, because if we can ignore friction, we don't really have to worry about anything in the y direction, because we don't have to worry about calculating the normal forces, which we would need to find the forces of friction. Okay, so I'm not even going to write out the second law equations for the y directions, because nothing interesting is happening there. I mean, Fn1 is balancing out Fg1, Fn2 is balancing out Fg2. This has got nothing to do with this question, okay? Because there's no friction, it doesn't matter. So I'm going to write out my second law equations, and I'm going to start with mass 1, and again, I'm only going to do it for the x direction. F net x equals m1ax. Determine acceleration. Is the object accelerating? Yes, definitely. In fact, we're given the acceleration. Okay, so the mass is 50,000. So we have 50,000 times ax, which is 0.5. And now I write out the sum of the forces. Now, it doesn't really matter. The coordinate system you choose never really makes a difference. We can choose whichever way the locomotive is moving to be the positive direction. Or we can say, since it's accelerating to the left, maybe we just make the acceleration negative. It really makes no difference as long as you're consistent. Okay, but basically you have two options. Either you can say, okay, it's obviously accelerating to the left based off of the FBD. That means that acceleration should be negative. And that means F engine should also be negative. And, I can just go from there. Or you can just establish a coordinate system where you say, okay, the locomotive, everything is moving to the left, so let's just say left is the negative direction. And again, it really makes no difference which coordinate system you choose. just for simplicity, I'm going to make left the positive direction for this problem. Again, it wouldn't change the answer to anything whatsoever, but let's just say left is the positive direction of this problem. And that means my 0.5 meters per second squared, I can keep that as a positive because it is accelerating to the left because I've defined that direction to be the positive direction. When I write down the sum of the forces, because I define left to be my positive direction, I write F engine, which is now in the positive direction, minus Ft. And this minus is just to indicate that this tension is going to the right, which is in the negative direction. Now, if you had chosen like a normal person coordinate system where right is positive and left is negative, you'd still get the same thing. You just would have had like Ft minus F engine equals 50,000 times negative 0.5, but you would end up getting the same answer either way. Okay, so again, makes no difference, whatever, blah, blah, blah. Okay, so we've chosen our coordinate system. I've written out my equation. Now I do the same thing for mass 2. F net x equals m2ax. Mass 2 is 10,000. And ax is a positive 0.5 meters per second squared because that's how I've defined my coordinate system. I write the sum of the forces, but there's only one x force on mass 2, and that is a positive Ft. And notice I have a system of equations here. I have F engine minus Ft equals, let's see, 50,000 times 0.5 is 25,000. And then I have Ft equals 10,000 times 0.5 is 5,000. And I'm all ready to solve my system of equations, except I don't actually need to do that because the question is asking me what is the tension in the coupling, and I already have that answer. Okay, that is just 5,000 newtons. Okay, my system was too easy to solve. Right, I didn't even have to do elimination because Ft is already solved right here. Okay, and so the answer to the question is A. The more interesting question to have asked would have been, what is the force from the engine inside the locomotive? Okay, so see if you can figure out what F engine would have been. That's more of an interesting question. And of course, if you solve the system of equations through elimination, you just add these two equations together. The Ft's cancel out. You get F engine by itself on the left, and on the right side, those add together. You get F engine equals 30,000 newtons. So that maybe would have been a little more of an interesting question. As it was written, this was a pretty basic question. Okay, but hopefully you're getting a better understanding of how to apply Newton's second law for two objects. Okay, pause it there. Make sure you add that to your notes. Okay, last example, example 3. Okay, now we have three objects, yay. Okay, so I will try to do this one a little more quickly. Example 3 says the system of blocks on a frictionless surface in the diagram below is accelerating at 2 meters per second squared. It's being pulled by a hand on the right, so it's being pulled to the right. Makes sense to have a coordinate system where right is positive, so we're back to normal person coordinate system. Alright, so just to speed through this quickly, I have M1, M2, M3. I didn't have to label it like that, but it just makes it easier to call it something. For mass 1, I draw the FBD. Focus on what is actually touching the objects. That's the key to these problems. Because somebody's going to be like, oh, the hand is pulling on mass 1. No, it's not. The hand is way over here. Focus only on mass 1. What is directly touching mass 1? The only thing directly touching mass 1 is this rope right here, this tiny little string. Okay, notice there's actually 3 strings. There's 1, 2, 3. So there's actually 3 different tensions. I'm going to call this first tension FT1. So the FBD would be FG1, FN1, and then this string right here, string number 1, is pulling this box to the right, And so I would have Ft1 like so. For mass 2, the FBD, I would start off something similar, force of gravity going down, normal force, blah, blah, blah. But now focus on the middle box. There's two ropes now. Okay, one pulling it to the left, one pulling it to the right. Okay, the one pulling it to the right is a second rope that's different from the first one. I'm going to call that FT2. But there's also this string pulling M2 to the left. But that's the same string we had in the last problem. And we already called that tension something. We call that FT1. There's that third law reaction force. Okay, equal and opposite reaction forces right there. Okay, so that's what the FBD looks like for mass 2. And then mass 3 looks very similar to the last one. We have FG3, we have FN3, we have the force from the hand, but the hand is transmitting it through like another rope or another string. I'm going to call that FT3. And then I have FT2, again that's the tension here, pulling mass 3 to the left. Okay, so that's what my FBDs look like. Okay, now I am going to write out my second law equations for each of the three masses. Actually, I will do it over here. Okay, actually, pause it here. See if you can answer this question on your own. Okay, so here is hopefully what you did. F net x equals m1ax. Is the object accelerating? Yes. In fact, we know we know what the acceleration is. So that would be 3.0 times 6. Wow. Times 2. I don't know why that 2 looked like a 6. We write down the sum of the forces. There's only one force here, that's Ft1. For mass 2, I have F net x equals m2ax. Okay, that is 1.0 times a, times 2. I keep missing that 2 for some reason. The acceleration is 2. It's given in the question. I write down the sum of the forces. On the left side, I have Ft2, which is in the positive direction, minus Ft1. And then for mass 3, I do the same thing. And so, of course, I end up with a system of equations. And generally speaking, this would be bad because then you would have 3 equations and 3 unknowns, which is not easy to solve without a calculator. But I don't think it's going to come to that. Yes, this is what your second law equation should look like. Now, I want Ft2 by itself. And so, the easiest way for me to do this is to use the first 2 equations and use elimination for the first 2 equations. So let me write this out. I have Ft1 equals, 3 times 2 is 6, so that's just 6. And then I have Ft2 minus Ft1 equals 1 times 2, which is 2. I add those 2 equations together. Those 2 cancel out. And I immediately get Ft2 equals 6 plus 2, which is 8 newtons, and I am done because the question is asking me for the tension in the cord at point X, and that is 8 newtons. Okay, and so given the same setup, I could have asked you about Ft1, I could have asked you about Ft3, here I asked you about Ft2, or I could have asked you about all of them. Okay, once you have Ft2, it's just a matter of plugging into the very last equation and solving for Ft3. Okay. So that is how you approach these problems, and you see it's the exact same process that we've done a million times before. You just have to do it for more than one object, and make sure you don't forget about the third law reaction forces. Okay, you can always spot the third law reaction forces because you see the same force showing up on multiple free body diagrams going in the opposite direction. So when you're drawing these FBDs, it comes down to getting the FBD correct. You just have to think what is physically touching that object and don't get distracted by things that don't make a difference. Okay, so in other words, the tension in the cord at X doesn't affect mass 1 because this cord is not touching mass 1. Okay, so when you're drawing the FBD for mass 1, this tension doesn't belong in that free body diagram, okay, because it's not directly touching that object. Okay, so if you just focus on what is doing the physical touching, that helps you get the FBDs drawn correct, and if you can at least get the FBD drawn correct, then you can probably solve the problem. Alright, so that is it for the rest of the semester. We are done with this unit. You should now be fully prepared to do any advanced cycle law problem that you see. As always, please let me know if you have any questions, and I'll see you guys next semester.